can be sometimes maybe directly on display, like in the case in this magnificent example, right? But it's also true that for many other different reasons that this lecture doesn't cover, basically, but the building has also disattached a little bit from the immediate context and from the environment. That is to say that the building is not really an isolated entity, right? It's actually an entity that is part of a network, that is part of a community of other entities of the same nature, meaning to say other buildings, but that it is also connected to a network, to a bigger a bigger network of relationships through energetic consumption, materiality, and its immediate context. So that's to say, a building nowadays, or well, even from the beginning of the history of buildings, has to consider its materiality. What kind of resources has it used to be built, to become a building? How does the building actually affect its context? Meaning, how does it affects other buildings, for example, right? By providing, in this particular case, for example, by limiting or enhancing the energetical consumption of the other buildings. A building also has a great impact in its community. And how much natural energy does it profit from, right? How much natural energy does it take? How much artificial energy does it consume from a network of energy consumption? That is basically something that is very well assumed in our days, right? That we can just plug a building to a network of energy, and the building will basically just provide for us heat or cold, or power for our microwaves or our lights. But it's the very act of us subscribing to such a network also implies that the building in itself is part of something bigger than itself, right? So if we translate these concepts from the ways in which the building is actually connected to its context, to its environment, we can start to talk about the different functions or different performances that the building can also have. In terms of materiality, the consumption in terms of material, what it actually takes for the building to stand. In this case, meaning structural performance, right? In terms of energetical consumption, both artificial or natural, how much does the building interact with the environment, or environmental performance, right? How much energy does it take, or how much energy does it provide in any case? And in terms of the context, right? How much impact does the building actually take? Does the building actually have in terms of the overall performance of its context? By casting shadows to another building, a building might actually be subtracting from the overall energetical consumption of a urban space, or by just by the main disposition of the building, it might have different consequences. That is something that I'm going to explain and talk about a little bit more in depth in practical terms in the examples. So that's to say, also, there's been recapping. There's been a rather complex shift in terms of how we conceived architecture traditionally, in terms of vernacular architecture, for example, which is an architecture that accomplished sort of equilibrium in terms of energetical consumption and in terms of the material manifestation of the building, eventually also resulting in a form that would actually go hand in hand with the local materials, and therefore also local construction techniques right? Resulting in a specific shape that would be the direct manifestation or the response to an environment, which is what we're talking about. And then later after many years, the decontextualization of such, right, where you can see actually a lot of buildings, a lot of the ways that we build nowadays can be perceived very repetitively. Sometimes can be we're basically not considering these very important factors anymore to produce our buildings for the benefit, often for the benefit of profit or for the benefit of economical motivation. Materially and energetically and urbanly, we have throughout the years somehow put these concepts, these very important concepts, aside in order to get the most of it. Now, if we look at other systems of ecosystems of structures, in this case, for example, the Selva Amazonica with the Amazonic jungle, which is one of the most extensive ecosystems in the planet, you can actually see a lot of the same principles also playing at hand, where most of these entities that you see here, like trees and these canopies and plants and animals, they somehow also have a same concept of competition or requirements, for energetic requirements to thrive. But in a way, they have also found a more stable equilibrium in between the whole ecosystem, which not only reflects in this particular picture, but it also reflects in the main morphology in which each of these, in the constitution of these organisms manifest, right? So that's to say, a tree, for instance, according to the requirements that it might have, right, both structurally and energetically, it's able to adapt its form and grow in the search for such requirements, right, structurally and environmentally, with the due process of adaptation. So you can see the manifestation of the same tree, for instance, in many different morphologies by the different requirements that it has in terms of its energy and structure. The same happens with birds, for instance, or many other animal species, in which you can see functional traits of their morphology, right? For many different types of birds and animals. So not only with specific function-specific traits like flying, but actually even, for instance, the same peaks of animals, right? Where you can see the same, the same great species, which is a bird, which has the same element, which is a beak, which has actually evolved for many different functions in different forms, right? So this I think can kind of start to paint the picture of how the form of things can derive from the function of things, which is what we're talking about, right? There's another great example from the same species, aerodynamics, where wings and the overall morphology of birds can be assumed that it's actually been derived from the function of the goal of its function, which is to fly, right? And this maybe might have come somehow granted by us throughout a lot of time, great part of our history. But when we start to incorporate simulations or even visualizations like the ones that we're watching now, we start to understand concepts like aerodynamics and computational fluid design. How can it actually take a part in us understanding why why the shape of a bird, basically the shape of the wings of a bird has this particular shape, right? The same goes for another species which actually use thermoregulation for energy economy. In this case, we're talking about energetical performance. For example, ostriches can keep their body temperature relatively constant and even throughout the environment, even though it can be a very hot during the day and cold throughout the night. They have an amazing thermoregulation system. And other animals, of course, through thermogenesis, which is basically the increasing of metabolic heat production, or vasoconstriction and vasodilatation, which is the shrinking or collapsing of blood vessels in a specific part of the ear of an animal, or insulation mechanisms or evaporative mechanisms, which actually allow for animals, including ourselves, our skin, to have an amazing natural mechanism for thermoregulation. So that's why, in a way, nature can be such a great example for this, because throughout many years of evolution, we have evolved these very complex systems of performance adaptation to our environment, which somehow makes us suitable species that are coherent with our context, right? Not only us as animals, but also trees and plants and nature in itself. Now, moving a little bit beyond nature, there are some other industries that have actually adopted these principles as well. And probably one of the most direct examples is the automotive industry, where the performance requirement is quite visual, or quite quite straightforward, because the primary goal of these entities is to be fast, right? The primary function of a race car in this particular case is to be fast. So throughout the history of race cars, like, it's kind of really nicely depicted in the picture of this actually simulation software. You can see how the complexification of shape of this entity, of this car, in the search of a specific performance, like in this case is speed, has somehow evolved, right, from the car in the top, where you can see not such a complex shape, but also not such an performative result. And then an amazing range of gradient of morphologies, including the variation of many different pieces of the same element, right, in order to achieve a better performance in this case. What is interesting is that actually in the same example of cars, in automotive, this speed performance can also be somehow quite tightly related to its energetical performance, because as you know, many of a car has to basically challenge or withstand its drag in order to overcome the friction that it has to be that it has to move through, and by that it actually requires power. That power comes from energy, and that energy comes from resources, which is basically always related to the context, even though that's immediate, like in the case of solar energy, or electrical energy, or if it's not so immediate, like in the case of fuel, right? But in any case, the point being, the more performative in terms of shape a car can be, the less energy it will basically consume, right? The more aerodynamic a car will be, the less effort it will take it to travel through through space, faster, but also with less energy consumption. So the point being here that the shape of things is actually quite important for certain performances to be measured or to be improved, depending on the function that we see. This concept, of course, has been adopted in many industries, not just the car industry. For example, the aerospace industry, in which, of course, a lot of inspiration has been drawn from nature, right, to solve issues, specific issues like aerodynamics or such. And I usually would play a video here that I'm not going to play today, which talks about how, you know, the bullet train in Japan actually had a specific amazing problem, which was that by being so fast going through tunnels, it would create what is called a sonic boom. And because the part of the engineering team included a biologist, it actually draw part of the shape of the bullet train in Japan, right? It draw inspiration from a specific bird, which is called the kingfisher, to adopt the shape of the nose of it in order to overcome these problems. Now, what you can see here in the images is something kind of in the same nature, but it's also very important to highlight here that biomimesis is not really the same as biomorphic, which means which one shouldn't really fall on the trap that we must actually copy exactly what nature forms, the forms of nature that are out there, right? One thing is actually to have the shape of the exact same shape of something, which is being biomorphic, taking the shape of something, and biomimesis is basically taking the inspiration from nature or the inspiration from the concepts that are in nature to be able to adapt them to different domains, like is the case of the aerospace industry and many others. Also talking about performance, but in this case structural, there is another example that is kind of rather more close to us, which is basically the design in the way that there are same bones are designed, right? And through this amazing principle of homeostasis, our bones are able to adapt structurally according to the different weight loads that we inflict into them gradually throughout our age, throughout our growth period, but also throughout different loads that we can inflict into these bones. So what you can see here, for example, is it's what's called the head of the femur, one of the bones that we have in our legs, which adapts its fiber, basically what is called the osteoclasts, right? That basically absorb and produce new bone tissues based upon the changes of loads that it carries, right? So as an example of somehow structural performance of structural adaptation, these type of principles have been also great, been adopted or abstracted from nature and transferred into our domain, which is architecture and engineering, right? And especially the methodological study of such principles, it's quite important. Principles such as topological optimization, right, where matter is only placed where it's suited, is actually been greatly explored throughout the history of design. Dating back to the ages of Galileo in the 16th century, all the way to the optimized truss by A.G.M. Mitchell 1 century ago, like the picture that you have on the right, where he began to actually use mathematical models to optimize shapes, right? So we're now talking about the transferring of these principles that I've been speaking about into architecture. And the visual result of these principles can be seen in great examples such as this one, the roof of the King's College Chapel in Cambridge, which where you can see, you know, beautiful architecture that is not only beautiful because of you know, its aesthetic appeal, but because it actually uses these optimization principles to create structure just where it's required, right? And it's quite if you're used to seeing you know, Gothic architecture or architecture from many centuries ago, this is not the classical way in which you would face things, right? But more even so, you know, taking that same concept forward, it's also widely embedded all over the work of the famous Italian engineer Pierluigi Nervi, such as in here in the Palazzo del Lavoro in Italy, in Torino, where you can see the same principle, but in you know, in a more high-end, modern, materialized terms. But even in another context, but even closer to us here in Barcelona, such same principles had already been doing this for a while ago, right? Such as the case of the Sagrada Familia, which is a great example of how, you know, form can be achieved through non-conventional means and for the same sake of performance, in this case, structural performance, right? Gaudí voice basically poses a question: what is the shape that architecture should take, you know, just by being inflicted gravity onto it? And I'm not sure if you guys have been lucky enough to come to Barcelona and visit the Sagrada Familia, but below the amazing building that is now under construction, you can actually come and visit the models that which Gaudí based himself for designing the building. And then the models look like this. They are actually hanging models of the Sagrada Familia, where you can actually see in a mirrored version of the building, because each of the shapes that each of the main shape that the actual cathedral takes comes from the comes from the shape that the catenary arches produces by hanging chains. They're really nice, amazing, complex models, and if you ever have the chance to come to Barcelona and see, this would be, I highly recommend it. Not only because of the the aesthetics and the creativity of this formal process, but it actually encapsulates in itself an amazing concept of performance that is quite simple, right? It was basically expressed by Hooke in the Hooke law, right? That as the chain hangs, basically the inverted form would be the shape that it would be perfect to withstand gravity. And that is basically the challenge of the construction of the Sagrada Familia, to build such high towers and such complex dispositions into one building that is going to be probably one of the tallest buildings in Barcelona, designed by Gaudí, in another age. This same mentality has been seen and proliferated all over the globe, not only the Sagrada Familia, for example, here in the Eden project, where by the biomimetic translation of certain principles, such as, for example, the wings of a butterfly, right? You can actually expand and cover huge amounts of area, and such as in the case of these amazing domes that are in the UK. But there are other amazing buildings taking this principle forward. Interesting efforts to bring natural concepts to design and for architecture and structural performance, specifically, such as the Barajas Airport in Madrid by Richard Rogers, or the Beaverton Library in Oregon by Thomas Hacker Design, or the same Stuttgart Airport in Germany, which was also designed by Gerken, Mag and Partners, but also engineered by Frei Otto, which I'm gonna talk about in a little bit. And even in the domain of design in smaller scale by this table, right, by Sililiu, where you can see an amazing resemblance of the structures that we have in nature being transferred in hierarchical structural models onto actual buildings, right? But all of these concepts actually come actually from shifting our mentality, right? From designing prescriptively to another way of designing, which is through form finding, right? Which is basically designing through physical forces and prototyping, which is highly involved in the work of the posthumous Pritzker Prize winner Fayotto, which throughout his career he spent a great deal of his architectural profession by exploring in searching material and structural economy through the study of what you can see here, for example, minimal shapes through soap bubble, as seen here in the left-hand side, which then manifested in architectural scale in various buildings, that you're probably familiar with, probably most notably the Munich Olympic Stadium in the right-hand side here, right? So from the need for performance, basically what we have is another approach to design, right, through form finding. Because this is basically an approach that somehow incorporates already physical forces in prototyping, and not necessarily computationally at this stage, but in this particular example of Fayotto, finding other ways to incorporate, in this case, for example, in the case of the bubbles of the soap bubble prototypes, material economy and material efficiency, right? What this shape that you see here is a minimal surface, which is basically the shape that will take the less material to cover this space, right? And here's a picture of Fayotto, which is coincidentally doing the same as Gaudí in his institute, trying to understand the form that takes the same process that Gaudí goes about, right? Through hanging models, trying to understand what would be the optimal form to resist vertical loads, right? And it's basically no coincidence, because it's basically the striving for the same, right? So the difference is that, whereas before it would take a lot of prototyping and a lot of effort to challenge these notions and to test these notions, nowadays, through the inclusion of computation, this is something that we can do in seconds, right? And this is now I'm entering another part of the discussion where the architecture needs performance. Performance has been part of architecture already for a long time, but there has been actually a great shift now in terms of the computational power that we have nowadays at our hands, in order for us to attain these same notions without having to go to the IAAC Institute, right? For example, and here I enter basically the question of how, what I was talking about in the beginning of the presentation, which is basically how the tools that we use or that we have at hand can constrain or enable or even challenge different aspects of the designs that we have at hand, right? You can see here Le Corbusier, first, drawing by hand, sketching amazing concepts that are embedded in I think in the core of many of the architects and architecture that we see today. And then on the right, there's that's his office, right? That was his office of architects. All of them kind of, drafting and producing technical drawings with the tools that they had at the moment, which was, a pen and a paper and a ruler and a technical table. And then the inclusion of CAD, of computer-aided design, which basically transferred all of these efforts into the computer, right? First, by merely replicating the same things that we were doing by hand. No, just basically CAD was at the beginning was just a straighter, more precise ruler, right? Like what you would see in AutoCAD classically, right? But then eventually we started to see architecture also as data, right? And nowadays, where what you can actually, the same model that it took Fray Otto in IAAC, months to produce or days even to produce, we can build in a very simple definition in Grasshopper in 2 seconds, right? And get a very nice approximation of what is the shape that gravity can produce into a form, by hanging it or by inverting it, like is the case, like we were talking with Fray Otto and Gaudi. And this is basically what the true power that we have nowadays at hand, that most of us, if you're a student, even more, you have access to such tools, not only economically, right, but in terms of the computational power that it requires for them to be run, and also more importantly, the knowledge that it takes to run this is widely available to you, right? As you can see, this I'm not sure how much you're familiar already with computational design. I'm sure you're very well versed, but the only thing that you need to make this simulation, which is actually a physical simulation done in Kangaroo 2, in the Kangaroo 2 plugin on the right-hand side. This is basically the composition that you have to make in this particular software called Grasshopper in order to make this simulation work. And this will take you less than 5 minutes to make, to get a very approximate result of the same. I mean, not only that, but we can actually take this, we can actually benefit from a huge ecosystem of tools that not only do Kangaroo physics, like the one, like you just saw before, but they do, a huge, a vast ecosystem of, they provide a vast ecosystem of simulation tools and design form finding tools for you to explore and benefit, which I would hope would be for the sake of performance. And this is basically what somehow the talk is about, is that the computational tools that we have now at hand, which are very widely available to you, should be used for performance, for striving for performance, which in the end turned into sustainability, right? So here we can see just basically a quick snapshot of a few plugins that are available in Food for Rhino, which is where the most of the plugins in Grasshopper live. But more than a specific promotion of this particular plugin is just to say that we have these tools available to us quite easily and with no great cost. These tools allow us to simulate growth, simulate behavior, right? These tools allow us to create very complex shapes that usually normally wouldn't be possible. Credits here to the steampunk pavilion in Tallinn, which was recently standing there in Tallinn, which was actually which is a feat not only possible just in terms of not only a feat because of its material complexity, but because it actually requires advanced tools for its fabrication. And in this case, for this particular pavilion was only possible to be constructed through the use of augmented reality for the formation and location of each of these bent planks. And this complexity doesn't necessarily have to be curvy or wavy or of a particular aesthetic, but can actually just derive from the main disposition, from the complex disposition of very simple shapes, like in this case, wooden struts that generate something very complex. And even beyond that, beyond the pavilion or the demonstrator scale, the same tools that I was talking about before, Grasshopper, for example, and parametric tools can be used to create, buildings as a whole, such as the case, for example, the Morpheus Hotel in Macau by Zaha Hadid, which great part of it was actually, designed and made with the same tools that you have in your computer today, not only in its very complex facade, but also, in the building as a whole. But coming back not only to formal complexity, but coming back to performance, how these tools actually affect performance. These are actually used to optimize material systems smartly for material economy, right? And a lot of this great work can be seen in the research of the Block Research Group in ETH, where you can see the deep study of what we were talking about before, the material economization, or basically material performance, which actually in here also incorporates structural performance and topological optimization, in order to come out with a shape or a slab, right, that would be optimized in terms of material to perform its function, which would be to withstand the forces that a slab has to withstand, right? And it's really amazing to see how digital tools can allow for these, upgraded versions of what we initially anyway saw in the King's Chapel, in the King's College Chapel material that I was showing before, or in the work of Pierluigi Nervi. Now you can see the refinement of the shape here, more complexly creating a better structural performance than the one that was created before. The same, some of the work can also be seen in terms of the material by the introduction of living systems, right? In this case, using mycelium blocks to create complex shape. And this is something, this also talks about material performance, because each of these blocks consume less energy than another of the usual blocks that we would used to be using for constructing such shapes, because they have been grown by nature, right? And more formally speaking, also the amazing work that's been done by the ACD and ITKE, which I think you guys are very familiar with. I had the pleasure to work in these two pavilions when I was a student, and I can, I can attest that beyond the aesthetic formality and final results and the aesthetical formality of these very nice pavilions, there is embedded a huge deep study on the performance of these materials and the performance of these structures, right? On the one hand side, on the left hand side, actually, an amazing effort to challenge and develop computational tools for performance, both materially but also computationally. And on the right hand side, actually being enabled only by novel fabricational techniques, like in this case of this bubble, a 6-axis arm robot laying in fibers inside of the bubble to reinforce it so that it can actually withstand when the air pressure is taken out of the bubble. What it used to take us before, even just a few years before, a very difficult process of simulation. In this case, CFD simulation. Thermal simulation through Energy Plus, right? Nowadays, can be very easily accessible by an amazing ecosystem of plugins and tools that are not only free of cost, but actually they're really well documented and available to you, right? Which create somehow lower the entry barrier for the use of these tools, so that we can start to incorporate these these simulations in these concepts into each of our designs without much effort, right? So here you can see a CFD model made by Ladybug, right? Just basically having a basic understanding of how the wind flows in a building can actually affect the way that you would dispose a building for energetical performance, right? These tools actually gives us not only gives us an insight in terms of the immediate context, the context overall where we're sitting in, where our project sits in, also gives us an idea of how it actually affects the whole urban or basically the whole context of our building, which is relating back to what I was speaking in the beginning, right? By subjecting our projects to, you know, wind factors or wind simulations or thermal simulations, we can gain an understanding of how these projects behave in their own context, right? And for example, this type of notions is something that we in IAAC, this is a picture from one of the projects that we developed from IAAC, inform not only the form that the building has, right? That in this case, a part of a building has, by adding computational fluid dynamic simulations to the design process in early stages, it can actually tell you which is the best behavior for the shape of a building. But it actually also, you know, the same notion applies to larger scale buildings, and especially, of course, when we're talking about wind and wind performance and aerodynamics, it has a huge effect in the way that it works with tall buildings, right? Aside from environmental factors, you know, plugins like Caramba and in Grasshopper allow us to quickly query different versions of structural elements, like in this case, you know, the parametric truss, which would, you know, how many elements do you actually need for this truss to work, and what is the immediate result of such element. This is at the palm of our hands nowadays with these tools. Now, just to, you know, towards the end of the presentation, I want to tell you a little bit of what we do or how we actually apply these concepts in the masters that I run in the MACAD by looking at two projects specifically, right? First, the usual methodology for us is that our students learn especially in the first module of MACAD is basically to try and gain an understanding of what is you know, what is the context that we're talking about when we're placing a building. So basically analyzing you know, analyzing a specific city or a specific site is important, and it also requires our you know, analytics as a human being or as an expert to read this data, right? But I would say that the most important part or the most you know, the higher note of all of this is that we're actually understanding architecture as data, right? So to start with, we start with data collected from the site, which we can visualize already by using Ladybug, for example. And this gives us an understanding already of what could be the particular requirements for a specific site, right? In this case, we're talking about Moscow because, of course, our students they're from all over the world, and they take and develop projects from the city where they're located. And of course, they gain understanding of the, you know, what are the main environmental factors that they have to address in their buildings in terms of you know, thermal and wind factors. But later on, they start to propose their buildings also in early stages of design, right? Inflicting their proposals through structural analysis through Caramba, which is basically the two plugins that I was speaking before, and coming up with versions of the same building, right? In order to then actually find metrics that they can use to check, you know, what is basically the least amount of material or material utilization that they can actually achieve in order to achieve their aesthetical purposes, or basically their intention, their final intention as a building. The nice thing about converting architecture or converting form to data is that it allows you to explore many different versions of the same building or the same concept. The way that by actually formulating a parametrical model that would actually encapsulate your concept, you can actually start to play with these parameters and start to move around these parameters in order to see different variations of the project, and actually submitting these variations to environmental analysis and structural analysis. You're able to come up with the one that is most performative in the way that you dispose, right? So if you're striving for energetic performance, that you might find the shape that is actually the most energetically viable. If you're striving for structural performance, you might find the one that actually has the least amount of materials according to the material that you specify. If you include both of these, then you will basically come up with a gradient, or or maybe a kind of a matrix of selection of projects, like the one that you see here, a catalog of projects in which you can choose what do you want to prioritize, right? And this, I would say, is basically probably the most the first approach that we usually have to parametric designs, but also performance-based designs. We actually we make a real effort to couple these two notions, so that parametric design doesn't just become a formal, a new style of representation or a formal outcome, but that it actually, provides us with data that we can actually analyze, so that we can actually compare and find the most performative version of our building, right? And this is important because I think, in my personal view, there is there is a lot of formality. There's a formal approach to parametric design, which is basically just the creation of complex buildings just because. But I think it's important that we have the conscience to actually include relevant data that is hand by hand coupled with sustainability, so that not only we can achieve complex shapes that look nice, but we can actually come out with the best version of our building in terms of the performance that it has, right? I'm moving forward to the next project, because I do want to leave a little bit of time for discussion in the end. This is another project, but this one developed more in the urban scale and in the third module of NACAT, which deals more with machine learning. Of course, the three modules of our program are always tightly related to sustainability and to creating tools, using tools first, but then also creating tools of our own that will basically challenge the concept of performance and sustainability in every scale, right? So from the use of parametric tools like Grasshopper, Rhino Grasshopper, and Ladybug and Caramba, to, in this final stage of the masters, the development of their students' development of their own tools through machine learning and web development, to have a different approach of analysis in every scale, but in this particular case, in the urban scale, that can be also later then brought to the final end consumer through web applications. So in this case, it's about providing the users of these tools a more comprehensive view of the city by calculating different distances of walkability and shifting the layers of the city, not only looking at the city as a set of distances that we can travel, but by including different types of building and amenities in these walkability traces that one can actually go about in a specific city. So our students have, they receive the knowledge basically to go through this whole complex workflow of collecting data through open source data sets like OSM, which is basically OpenStreetMaps, right? Where they basically collect this data, they clean it, and then basically through network analysis, they find different walkability scores. And then by using unsupervised machine learning, they start to cluster these scores into segments that are actually they later on pour into the web, right, into Mapbox, so that they can actually visualize and propose new location and type of amenities in a specific city. All of this is a complex process that, of course, is quite intense. It's quite, and we move away from being the user of parametric tools to somehow being the creator of tools that are not existent, or putting together pieces of different different bits and pieces of code and parametric tools to create something very custom for something very, very complex. Like in this case, through a machine learning model, using first unsupervised learning model for clustering, and then a supervised learning model in parallel for classification of these different areas of the cities, so that we can have a model of classification for all of the different walkable paths of a specific aspect of the city that our students want to investigate. Now, I wanted to include this because I think it's the only way to look at this type of project is by actually understanding, becoming a little bit of a data scientist and starting to look at these high dimensional models in a way that we can actually analyze and display. So they learn about database representation of through scatter plots and per plots and heat maps by using different indexes of correlation coefficients to understand which attributes are related to each other, right? And all of these analyses that are somehow might seem very complex, it's actually really helpful then later on to basically, for example, how much iterations should the supervised learning model should have. All of these analyses are helpful for our students to become no longer the consumers of these tools, but the providers of these tools, right? So that the end user can actually have have a view of the city that is not the common view of the city. They can actually see where in the city is basically all of the health aspect of the city is located. Where is the educational cluster? Where is the recreational cluster? And different type of categorical categories that our students want to investigate in the city, for which they collect data from, and then a set, they bring it eventually to a website so that it can be used by users. This is important for me as as an educator, but also as a researcher and as a developer of tools, that our tools, the tools that we develop, both in this project, but in most of our projects, usually become apps or tools for consumption that can be useful and can be useful, or can be consumed, or can become part of the way that we actually see cities nowadays. So as I said, I did wanted to leave a little bit of time for discussion, and I want to wrap up then. This is my contact. You can feel free to contact me, through social media or directly through my email. Or if you're interested in our program, of course, a little bit of self-promotion, you can always reach out to us online. I hope there's a little bit of time for questions or discussion. As I said, I felt like I was already going a little bit overboard.
Okay, thank you, David. I think it's really interesting and also a comprehensive lecture, covers the development of digital tools, particularly related to performance-based design. well, I think in lecture, David not only introduced the basic kind of the concept of the performance-based design, which is highly related to kind of biomechanics and how we learn from nature, and to see how form is interact with his environment to find his best kind of the performance or his best form in terms of the dialogue with the environment, and also introduce a lot of kind of cutting edge development of tools for not only students but also for practitioners to really kind of cultivate a kind of performance driven design process to get the best results per se. Yeah, right. Also introduce kind of two of their projects. I think AIAC has really kind of covers different skills from kind of installation to architecture and also to urban skills to really kind of embed digital tools in those practices. I think that's really amazing. So I think we still have plenty of times. Let's see if any students from the floor have questions.
Thanks. I think it was that was a really nice summary of the whole presentation, and indeed, I'm happy that the core of the message came across. I mean, I'm happy to answer any questions, and you guys feel free to raise your hands, or if you're around. I'm actually would be really curious to see, how much do you guys engage with computational tools, and if you actually have these concepts in mind when you learn when you want to learn computation or want to learn about parametric design, if this is the first thing that you have in mind, or eventually, performance or sustainability is something that you also incorporate in your work through computational tools.
Well, I think most of our students are well in this class they are kind of the fourth year of their master program. So in China, I think the students, the undergrad students, they really I would say like half of them really mastering the kind of the parametric tools, the digital computation, those kind of tools, but they usually use those tools to do design studios, meaning to design a kind of a building project, not really engaged with how you use those tools to do a research-based project or even a pure research. But so they just start their program and just learning how to engage this kind of paradigm of research in the field of digital. So if you have any questions, you may just okay.
There's a question in chat. I will read it. Okay. Thank you for the lecture. You're very welcome. I have a question. I'll read the first one. The response of organisms to their environment is usually based on a closed loop system. When the environment changes, the organisms may change accordingly, just like the growth and fall of leaves. But building-based simulations of the environment are usually one of instructions to achieve a certain goal. For example, first we make a judgment about the building environment, and then we design and build it based on that environment. But then it doesn't change for the environment again. How do you see the difference between the two? And hold on. And will the ultimate outcome of genetic language of architecture be interactive architecture? It's a really interesting question indeed, and I think that there is. I mean, you're right. Of course, the way that we know buildings nowadays is quite static, no? So we can only read. We can try to get a good read of the environment and through simulation And through, the different technologies that we have nowadays, we can actually get a really good read of the environment. And then we can propose the best way to to engage with the environment, and basically, somehow, hopefully not engage, but actually, communicate or, merge with the environment with the least amount of impact possible. No, but it's true that the environment changes and the building doesn't change necessarily. But this is something that I think we also aim to tackle here in IAAC a lot. Is this the notion of the building in itself? No, not only in the way that the building is conceived, but in the way that the building behaves, right? And also in the time span of the building. So I think there's these two variables that at least we can play with that are interesting to investigate. Basically, how much does a building need to last, right? Our environment is ever changing, and it changes in a very slow pace. And our buildings usually last for what, 50 years, 100 years. So the notion of architecture and how ephemeral is it, I think is a parameter that we can also challenge, right? Do our buildings have to last for 1,000 years, or can we make buildings that are more, can we make buildings that we can put up and dismantle or change, right? When it's possible. And we are there. We enter a really nice discussion about concepts like such as circularity, for example, design for disassembly, where you can actually challenge the same longevity of the building in itself, right? Maybe the building shouldn't last for 100 years, and maybe it should just for 20 years, and then the phase of adaptation of building construction is a little bit more agile, right? But then and then there's also a second response to a constant ever-changing environment, which is basically dynamic architecture, right? And architecture can also be dynamic and can also have a behavior, not just a structure. And that means certain part of the buildings can actually adapt to the environment in an adaptive way. Within this aspect, there are many interesting currents. For example, there's a lot of work being done in the IAAC, which is the institute that I studied in Stuttgart, about adaptable facades, lightweight dynamic facades, passive activated facades, facades that basically change with no energy by material composition. And then there's also even the incorporation of nature into the building, right? And the work of Ferdinand Ludwig, for example, in Baubotanic, where you can even start to think about buildings that incorporate nature as an adaptive resource, as a resource for adaptation, right? Using plants and trees in themselves as part of the building. So I think the question is super relevant, and the important thing is to challenge these questions freely, in a way, right? To think outside of the box and think, why do buildings have to be like the way that we build them today? Why do they have to last the same, the years that they last now? Can they last less? Can we find a better way to put them together and easily bring them down without wasting much resources, so that we can find another way for adaptation? Because in the end, the key word is adaptation, right? There's an environment, it's changed, the environment adapts and it changes. How are we going to come up with responses of ways to adapt to this environment?
Well, yes, I agree. I think that the question is really a profound question. Oh, I would add something. For example, even for those adaptive architecture, which could kind of evolve after his construction. it still cannot kind of truly interact with this kind of dynamic environment because we certainly don't have those computational power to really predict the interaction, the feedback loop between architecture and its environment. That's how in the 70s the architecture machine group they failed because they simply we still cannot do I would say.
Hmm.
But it doesn't hurt. We use those tools to simulate the environment in a reduction way because we need some kind of evidence for us as architects to make decisions in certain criteria. So that's how it helps us. Even it's not really truly simulate the environment, but I think it's enough for a certain period of time to make the architecture better than other versions of design results.
I agree for sure. What we have, I think we have on top of it, I think what we have as an advantage now is, I think part of what I wanted to convey in the lecture is that because we have these tools available to us nowadays so easily, we also have a little bit of a responsibility to challenge these questions nowadays. No, I mean, we no longer can just propose the same buildings like we were doing 1,000 years ago. No, we also have, because now we have so much data of the environment, so much data around us, and so much data of the impact of the building in itself. We also have a little bit of responsibility to ask these questions that you're asking now, no, and to come up with a response the best way possible.
Yeah. Okay. Let's move to there's another question. Thank you for it's in the chat box. Thank you for your lecture, David. I have a question. We know there are many vernacular architectural techniques in rural buildings outside of the city. So the techniques sometimes show effectiveness of improving building environmental performance, which may originate from the adaptive evolution of construction techniques in the heritage. We have seen that advanced computational method can help us reproduce Gaudi's thinking about structural performance in terms of environmental performance design techniques in vernacular buildings. Is it possible for advanced computing method to effectively extract their principles and turn this ancient empirical method into modern or else into contemporary practical method?
I think this is also a good one because I think here it also touches a little bit about the conversation of the agency of the architect and how we are much better equipped sometimes to make certain analysis and decisions than the machines, no? Because I don't think I don't think I'm a technologist and I'm an advocate for technology, but I think there are a lot of things that machines will never do as good as we do, and that is basically somehow exercises of abstraction and conceptualization of things. And for example, if you're talking about extracting principles from vernacular architecture, I would think a student like yourself, right, or from a student from another part of the world, is much more suitable to research about vernacular architecture and come out with the principles that you need to extract in order to transport them or basically transfer them to computational models, right? So, and this we do all the time actually in not only in IAAC but everywhere. There isn't a little bit of a trend. It was called digital vernacular, which is basically revisiting a lot of concepts, materials, technologies, even ancient technologies of that somehow have been left behind without much question, that are worth taking a look back into, right? For example, bamboo comes to mind, right? But the bamboo construction is something that we have probably learned more about throughout the years because of just because of empirical knowledge that we have built. And even though it's probably not scientifically documented as other materials, like you would say concrete, I think is something that we can learn a lot about by actually revisiting a concept and learning from techniques that have been developed in the past from bamboo construction. No, and if you couple that knowledge with which would give you somehow the constraints for implementing that in computational tools, simulations of material behavior of bamboo, for example, and such, I think it's really powerful, right? Because you don't start from scratch. You start already from a base of knowledge that has been backed by years and years and years of trial and error. I don't know if you agree, Chao.
Yeah. Well, I think there's another perspective of well, with those kind of contemporary tools, I think, for example, the simulation tools, those kind of visualization tools, it could also help you to see those kind of ancient principles of construction or spatial organization from a kind of new view, to really understand them in a kind of more profound way, and then to maybe you may extract more kind of principles, let's say, than people who studied them without those computational or digital tools. For example, there's a new trend called digital culture, which is using to be honest, I still have doubt on those, but there's a group of people, they use digital tools to analyze texts, like from poetry or from kind of those kind to understand, to try to extract some more understandings of those texts, without reading them. I think we those kind of paradigm, it also kind of give us some new perspectives to about studying space, about studying buildings.
For sure. I think it's important though. So that one thing that we have as architects, and we're not data scientists, right? No, we this is the thing. I think there is actually another domain that deals with data and that deals with computation that is much more efficient about that than us. But we have what we have as an architect, I think, is this domain understanding of the trade that allow us to have a better interpretation of things. And the thing about architecture is that is a domain with so many subdomains. It actually is really complex. And when, for example, in the making of a building, there are so many participants in the making of a building and so many aspects of making a building in itself nowadays that it's very difficult to I mean, the architect has an overview of this, and it's very difficult to somehow even have these domains talking together. So it's very difficult to somehow datify the whole building process. This is where we enter the BIM paradigm and everything, like building information modeling and such, and it's still a challenge. But what I really wanted to say is basically that I think the perfect team is being technologically savvy and knowing where to use your tools, but also knowing where you have better agency than a computer, right? You have you have a better criteria for certain things because you have experience, because you have experience in you have have five senses, you have a lot of memory, and especially you have an understanding of the context that the computer is very difficult to understand, and the context is super complex. No, I mean, we can gather data, as much data we want nowadays, but we will understand temperature and wind and maybe scientific factors, but you have a cultural knowledge of the context, for example, that is very difficult to understand. And this, I think, this is where it's very difficult that a machine will become as good as a human eventually, but that's my personal opinion. And I think we have another question and maybe a few minutes. So if you want, I'll read the next one.
Yeah, okay.
Thanks for your lecture. You're welcome. May I raise a question? It's mentioned that the involvement of computation powers the simulation generative design, which had realized the automation in optimization. In parametric design is an important step of optimization, which means we have to propose a general description of buildings or cities. Is urban planning and design in urban planning and design, is there a standardized and unified morphological description of the city? I don't think so. I think I would say actually the opposite. No, I think we have to somehow run away from this standardization and unification. It's basically like the case of the birds that I was talking about. No, imagine the city can be the beak of a bird, and according to the different contexts or the different functions that a theory requires, it should have a different morphological description. Of course, you can probably try to get things, find points in common of every cities, and you will find elements that every city has, right? Problems that every city has, like transportation, mobility, and elements that every city has, like buildings and transportation means in citizens. But overall, I think it's about reading the specific requirements of cities, not only in terms of environment, like where the city is in, but a lot in terms of what is available around it and what is the cultural background of a city. So I would think, as to answer your question, we should strive for more a non-standard and non-unified morphological description of the city, but something that we can, something that actually reflects the function and context of the city, the same as the beaks of the birds. No.
I think I totally agree. I think I think it's really a difficult question when it comes to using for example parametric tools for the optimization of urban morphology, because we know the so-called continuous variation is the basic principle of parametric design. So when using those two, I think the students' concern is when using those tools to really do a kind of urban master planning of our city, it usually gets results which, although it has kind of variations, but the basic kind of let's say the typologies is somehow unified. We have one basic prototype and it varies according to the environment. But I think the not solution, but we always can kind of combine the typological thinking with the computational thinking in terms for those urban design. So it's just a different of strategies.
I agree. And I think my answer to the last question, which I already read, and I'm sorry, but I will have to leave in a few minutes, but I do want to answer this last one, is also related to the previous question. And the question is, do you think that the current parametric design process and tools somehow limit the capabilities of architects to think outside of the box? what do you think would be an optimized working method to fully embrace the emerging tools, other than introducing more context input parameters? I think, so this, I think, to me is a great question to wrap up the lecture, because a lot of what I showed today is somehow kind of an introductory lecture to parametric design and computational design. But eventually, I mean, through my own experience, I was allured by computational design because, of course, first, the formality of it is really appealing, and then you start to understand that basically, by looking at architecture or design and then geometry as data, right? You can actually start to propose different relationships in between architecture and context, or even in between architectural pieces that you wouldn't see before when you're projecting, the more traditional way. And this is basically the story of how you, through the use of your tools, are limited by what you can do, right? It's very difficult to actually understand all of this in a pen and paper, right? It's easy to conceptualize a building in a pen and paper. I always require that my students, they conceptualize things in pen and paper, because that's where you need to do them. But if you want to really understand complex things are really complex, or complexity, and that might mean something more context input parameters like you mentioned, then I think you have to break the tools that you have, and you have to escape out of the tools that you have. No, let's talking about Rhino and Grasshopper. Grasshopper allows you to create your own tools, for example, and develop your own plugins. And that's already fantastic. No, that means if you find something that is not there for you, that fulfills your needs, you can make it on your own. And I think that's an amazing next step. But even beyond that, what we strive for is that to also empower the architect and the designer, not only to design and ask these questions, but actually to make the tools that they need to make things. And that's that basically ends up in the architect becoming a programmer nowadays, and the architect learning computational skills to make tools, to analyze, to learn what are the current technical possibilities at the core, right? So that they can actually challenge technical possibilities, and don't let the design tools constrict their purposes, right? I think that's that's probably going to be the final question that I can answer, because I have to run.
Yeah, sure. I see it's a great lecture, and also we have many questions from students. It's a great dialogue and covers a lot of territories. We won't spend more time. So thank you, David, again for the lecture. And for next week, I think we have your colleague Alex to give the next lecture of the lecture series. So thank you again, David, for your time. And
you're very welcome. It was really nice pleasure to be here with you guys. Thanks a lot for the interesting discussion, Zhao. And I wish you luck. I hope that you think about, this can be material for reflection for you guys. And also I hope that you feel free to approach me if you have more questions, or if you have anyone where you want to continue this discussion. I would love to. So good luck to all of you, and thanks a lot for the invitation again.
Thank you, David. Bye, everyone.
Bye. Ciao.